Here we go. So today we're going to go and apply complex numbers. Most importantly, we're going to go and apply these complex numbers in a particular area, which is mostly used in electrical engineering, but also anything that has to do with electrical and in that field of a career or jobs that are used to read those kind of maps. Now, we're going to go ahead and keep it simple. So we're just doing a simple type of circuit or a simple type of diagram that we're going to be reading and identifying the parts to here. So with that said, we're going to go ahead and stay in complex numbers. We're going to have both my real part and my imaginary parts. We're going to go ahead and continue to see them in standard form. And we're now going to apply them to a electrical circuit. Now, different parts of the circuit are existing here. One of them, obviously, we have to have a power, so we can have a battery or any type of current that we have given to it. But we have a wire, and then we have anything that's connected to a wire and certain types of resistors and inductors, depending on how much or what is connected to that current or that circuit in order for it to function properly or for it to do what it needs to be doing. So here's a diagram. So here's what it looks like visually. And this is how it looks like as a diagram once we just translate everything to a diagram. And it's showing whatever it's supposed to be doing. Now, there's certain type of sophisticated circuits or basically components of where it could be located. And yes, it can be programming or any type of programming type of chips or components here that have to be connected to it. But those are more sophisticated. We're going to go ahead and keep it simple here because obviously we're going to go ahead and just be focusing on the complex part of it or the complex numbers of it. So we have certain parts that we're going to be focusing, like I said. First one is a resistor. The second part is an inductor, and the third part is a capacitor. Now, the way that they look like in a diagram are as follows. A resistor kind of looks like a is it EKG? Like reading? You guys have seen them? You know? Yes, your Z line. So basically, they're going up and down line, like zigzag lines. Your inductor, whenever you see them on the diagram, they're going to look something like a coil. So it's going to go ahead and do little circles. And your capacitor is going to look like a little storage box. So basically, we're storing some energy in there. Now, each of the parts here in your circuit are going to have different purposes. More especially resistor is going to continue or do the current. It's going to manage it. The inductor is going to save or conserve some type of energy. And the capacitor is going to serve or store another type of energy. So some of them are storages, they control, and then the resistor obviously manages how much goes through. So this is how they're represented in mathematics. A resistor is going to be represented by a real number. Now, a real number is any number that's on the number line. You guys already know. Anything that can be graphed on the number line. So it can be a whole number, it can be a decimal, it can be a fraction, it can be a square root, any rational number. It can be indefinite decimal value, anything that can be graphed on the number line. So it can be a real number. I'm going to go ahead and write R for real number. My inductor is going to be an imaginary number, but the coefficient of the imaginary number is going to be greater than 0. So what are my values that are greater than 0? Any positive number. So this is going to be a positive I. Now, my capacitor is going to be another imaginary number. However, this time it's going to be represented by a number or a coefficient where it's less than 0, which is negative number. So we have a negative I in this case. So we have our real number, positive imaginary number, and a negative imaginary number. All right. So with that said, let's go ahead and see. Now, just very quickly, what they do in their functions. A resistor is going to be a component that obviously regulates. It's going to show or it's going to distribute that energy so that it regulates it. Our inductor is going to store a type of energy. Our capacitor is going to store another type of energy, okay? So we have storages and we have regulators. And this is what they look like in real life. So if you ever see a diagram or you see them in real life, this is what you would see on a circuit, okay? You're going to see your capacitors, resistors, inductors, and these are the various types of them being made, okay? All right, now, our first example, we're going to go ahead and stay with the diagram. Let's go ahead and label the parts of the circuit. We have our beautiful parts. So what did we say our zigzag looking like diagram would be? It's going to be a resistor. So we're going to go ahead and label it as R. Now, what did we say our beautiful coils are going to be?
Indicator.
Not indicator. Inductor. So we're going to go ahead and represent it with an I. And our last part, it is, oh my goodness gracious. Our little storage box. Again, it's storing energy, guys. It's our what? Our capacitor. Yes, it's a negative I. So we're going to go ahead and have a negative value on that side. All right. Okay, so let's go ahead and get used to the diagrams here. Everybody has that? Perfect. Okay. All right, so let's go ahead and identify the parts. Here's the next diagram. Go ahead and label the electrical circuit. Let's see if you can identify the parts. So go ahead and pass it on. All right, Bayani, help me identify one of the parts here. Let's see. What is this one right here? A capacitor. Do we identify another one? To the right. Okay, another capacitor. All right, pass it on, Bayani. Andre. What else do we identify? The resistor?
Yeah.
To the right. Right here, we have a resistor. Do we have another one?
Yeah.
Right here, resistor. Woohoo. All right, and the last one, Andre, pass on. Angel. Where's the eye? Not indicator, inductor, guys, inductor. Goodness gracious. The beautiful inductor. Now, anything that you see with a plus or minus sign, guys, is going to be a battery. It's going to be anything that gives the power onto the circuit. Now that we identify the parts, let's go ahead and see. Now, in real life, obviously, this is another more sophisticated type of diagram. However, can we identify the parts? By looking at it, this would be what? Not the inductor, guys. The inductor. What about this one? The resistor. And this one? The capacitor. All right. This is more sophisticated one. Now, electrical circuits. Let's go into the currents. One current that we have here is alternating current. The second one is direct current. Do you guys know what type of current is alternating current? You can go in either direction, but what would be an example here in the room?
Like a chili.
It could be a fan or what? What else? The lights or the outlets, anything that we have to plug it. Our beautiful. Oh, goodness gracious. Electrical devices. All right, direct current would be a battery. So you guys all have those type of direct currents in your phone. You guys have them nicely and neatly charged. They have batteries inside of them and their direct current included into them. Now, the type of current or the amount of current that it's going to go through your circuit is going to be called an impedance. Okay. And it's going to be measured in ohms. So that's just the unit of measurement that we're going to go ahead and use. So we're going to go ahead and figure out how much current goes into it. And it's going to be measured in ohms. So we have two types of current. Alternating current and direct current. Okay, now these are just examples. All right, everybody has this?
No.
And it's impedance, not independence. Y tampoco indicator.
That's sticky.
Ay, conductor.
I need to know.
Okay.
Remember,
I know as indicator.
my goal is to make you say it.
Ay, inductor. Okay, here we go. Ready, ready? All right, let's go ahead and find the impedance. Impedance. Let me go through this really quickly. All right, so let's go into example number 3. We have our beautiful diagram. We know what each part represents. We have a real number, imaginary number, another part, component, imaginary number, but negative value. Now, here's our example, our diagram now with values. We have our voltage given here, 120. We have some parts or some of the components of our circuit. We're gonna go ahead and find its impedance. Now, the way that we can find this is by looking at the diagram and its image and looking at the values that are present. So for example, resistor, we have a resistor right here. And that one measures how many? 4 ohms. Now, this one's represented by a real number, so this one's just going to be positive 4. Okay. My inductor is which one? The one that looks like a coil. So I have my inductor. It's going to be an imaginary number. And its measurement is what? Is what? 3. So this one's going to be 3I. And the last one, the capacitor, is going to be 5. However, it's measured by negative I. So it's going to be negative 5I. Okay. Here's the capacitor. So we have a resistor. It's 4. So it's 4. My inductor is 3, but it is an imaginary number. So it has to be 3I. My capacitor is 5. However, it has to be value of less than 0. So it has to be negative I. Remember those terms, okay? All right, now combine them all together. What would we get? Not 2. We have a real number, 4, and then we have 3I minus 5I minus 2I. So its impedance would be 4 minus 2I. Not too bad, right?
That's so hard. We should do this like the next.
Yeah, okay. We're gonna do it for the rest of today. All right, ready? Everybody has this? Okay, let me go ahead and clear. All right, go ahead and try this meal. The next one, example number 4 on your own. Go ahead and write the impedance of the components, your resistor, your inductor, and capacitor, and go ahead and find the impedance, the total impedance of it. Okay, let's see what you guys get. Beautiful values here. Or let's go ahead and identify the parts first. Which one's my resistor, inductor, and capacitor?
9.
Okay, so we have resistor,
Inductor is indicator. That one's gonna get the one to the right, and the capacitor is gonna be the 10.
so we have our beautiful capacitor. All right, now what are my values here? Caleb, pass it on.
Your first one is 9,
9,
and your indicator is 7I.
7I,
Your
Inductor.
capacitor is negative 10I.
negative 10I. All right, what is my impedance altogether? Pass it on, Joe. Minus 3I. Raise your hand if you agree, guys. Our place. Correct. Awesome. Okay. All right. So how do you feel about these now? Identifying the parts, identifying the values, the measurements, and everything else. Ready to step it up? Okay. Yeah, we're ready. Okay. We are ready. Okay, now I'm gonna go ahead and talk about voltage. Now, voltage basically is that amount of current that's going on. So yes, we can measure it, but how much do we have it? Or how much do we have of it, sorry. We're gonna go ahead and do that by multiplying the current that's already there by the amount of impedance that exists on the current or the circuit that's given to us, okay? So go ahead and write down your formula. So we have V equals your beautiful current, which is your I, times your impedance, which is your Z. And we're gonna go ahead and find out what the voltage is in total, okay? First for each component, and then all together as a circuit. So we have our beautiful voltage. Okay, how much of it do we have it? We have it there. Now, how much of it do we have? For the current, how much voltage does the current have? Okay. Lisa. All right, here we go. So here is our next diagram. So we have an example number 5. All that happened is that we added one more component to our table. So yes, we do have our components. We have a resistor, inductor, capacitor. We have the impedance. So we're going to go ahead and measure it from the given diagram. But we're going to go ahead and figure out how much voltage is for each resistor and then all together. Okay. So not resistor, through each component. All right. So for the first one, which one's our resistor? 4. So we have 4. Which one is our beautiful inductor? 3I. And our beautiful capacitor, I'm gonna do it in green. It would be negative 5I. Now, all together, it would be what? 4 minus 2I. Okay. Now, let's go ahead and figure out the voltage of each component separately. We're going to be given the voltage, or sorry, the current of 24 plus 12I. That's just an example. It can be anything that's given to us, but in this case, let's say that we have this, for example. So I have my resistor. I have 24 plus 12I, and I'm going to multiply it by its value. So it's 5. So very simple. Let's go ahead and distribute. We're left with 24 times 4.
26.
And 24 times 12I. 48I. So the current that's going on, or the voltage that's going on through the resistor, is 96 plus 48I. Okay, let's go ahead and do the same now for the inductor. We have 3I, 24 plus 12I. All right, let's go ahead and do the procedure. Let's go ahead and distribute. We have 3I times 24. 72I. And 3I times 12I. 36I squared. Let's go ahead and simplify that. Negative 36 plus 72. Beautiful I. All right, the last one. Negative 5I. And we have our beautiful given current, 24. My 24 looks like a 9. Let me go ahead and fix that. Plus 12I. Distribute. Negative 5I times 24. Negative 100 and. Negative 120I. And negative 5I times 12I. Negative 60I squared. All right, let's go ahead and simplify this very quickly. Negative 60I squared becomes positive 60 minus 120I. Not too bad, right? All right, and the last part. The bottom part, don't forget about this part right here. Altogether, 24 plus 12i. All right. So what would be my first step? Distribute, so we have 24 times 4,
96.
we have 96. 4 times 12i,
48,
positive 48i. Negative 2 times 24,
negative 48.
negative 48i. And the last one, negative 2i times positive 12i. Negative 24 I squared. All right, what happens to my 48i and my negative 48i? They cancel out and we're left with 96 minus 24. Let me go ahead and go the long way. So minus 24 times negative 1. This becomes a positive and a positive. So therefore I have 96 plus 24. And it gives me 100 and beautiful 20. All right. Not too bad, right? Not too bad? Too hard? A lot of multiplication to do. Okay. Everybody has that? Go ahead. Yes. All right. Let me go ahead and clear. Everybody have that? Okay. All right. Let's go ahead and try the next one on your own, guys. Let's see what you guys get with number 6. Now, this one has several parts, but what do you think is going to happen to all the parts? They're going to go ahead and be combined. So go ahead and combine them and then find your voltage for each component and then find the impedance and the total voltage. Let's see what you guys get. Our resistor. So we have a resistor right here. Do we have another one? On the right, another resistor. The top two are my beautiful capacitors. And the last one is my beautiful inductor. All right. Now, whenever I write my impedance, I'm going to go ahead and combine the corresponding parts. So how do I write my beautiful impedance for each component? Pass it on, Tessa. All right, Brianna. My resistor is 6. I have 4 plus 2, which is 6. 3i. Negative 5i. So I have 2 and 3. So therefore combined together, I have negative 5. Beautiful I. All right, now that I know each of the components, let's go ahead and find the voltage for each component. Pass it on. All right, draw.
It's gonna be 6 minus 2i.
So I have altogether, it's going to be 6 minus 2i. Perfect. The resistor.
That'd be 6 and then 18 plus 6i.
18 plus 6i.
50 plus 108 plus 36.
There you go. 108 plus 36i. All right, pass it on, Joel. Victor, what's my next one? 3i. Let me go ahead and write it out. And then I'm multiplying it by the beautiful current that's given. So it's 18 plus 6i.
It's negative 8 is going to be that. That's
Mm.
total, but 54i was
54i
plus 18i squared.
plus 18i squared. And then it turns into negative 18 plus 54i. Woo-hoo. All right, Victor, pass it on. All right, Angel, the last one. negative 90i plus 30, negative 5 times 6 is negative 30i squared. Simplify it and we get what? 30 minus 90i, all right. And then all together, pass it on, Angel. Joaquin, there you go, Joaquin. 18 plus 6i, there you go, we're gonna go and multiply all together. So what do we get? Which is? What is 6 times 18? 108. And then 6 times 6i, so we have 36i, negative 36, positive 36i. The next one, negative 2 times, negative 2i times 18, negative 36i. And the last one, negative 2i times 6i, 12i squared. All right. Now the last value is going to become a positive 12. And what happens to my 36i and my negative 36i? They cancel out. So I'm left with 108 plus 12, which is 100 and beautiful 20. Raise your hand if you got that. Yay, all that work. All right, how do you feel about these now? Not too bad. All right.